Hello, my name is Colin Ngo, and I'm from Section C of Physics 2211, and I'll be talking about Lab 3, black hole and orbits. So the lab was broken up into two parts, Part 1 and Part 2. The purpose of Part 1 was to find the mass of the block by analyzing an orbiting star's mass of the black hole, by analyzing an orbit star's motion and its net force at several points in time. Part 2 was to experimentally determine the required initial velocities for a spaceship to maintain a stable figure-8 orbit around a planet and a moon, and we did this by analyzing the net forces acting upon each body within the system. So just quickly, results preview here. This is part 1. Our mass ended up being 1.4 times 10 to the 34 kilograms, and this is our code here with our black hole, our star, and then the vector arrows, as you can see. Part 2, the pink showed the spaceship's path, the light blue is the moon's orbit, and the dark blue is the planet. As you can see, we couldn't achieve that stable figure-8 orbit, but we did prevent the spaceship and the moon from crashing. So just an introduction of fundamental physics principles. We have Newton's second law and gravitational force. We start with Newton's second law here, and we equate that equal to change in momentum over change in time. And eventually we would get to this equation where F net equals the addition, or the sum, of force parallel plus force perpendicular. And this is just through a bunch of substitutions in a series of derivations. And then that's our final equation here. Also, we have the gravitational force formula, and we substitute F grav here for dp over dt, and then we can solve for mass 2, which is the mass of the black hole, and this is how we find the mass of the black hole from part 1. And we use both of these for both parts, So for our lab setup here, materials are the glow script code, and our assumptions are that there are no external forces acting, so no stray asteroids or anything else. For part 1, our system is the the black hole and the star, and then for this part 2, it is the moon, starship, and the planet, and the surroundings are just nothing else because we assume there are no external forces. The units are standard units of meters, kilograms, and seconds. And for part 1 here, we would start with the initial conditions where the G constant is equal to 6.7 times 10 to the negative 11. We have the mass of the star and our delta T, which is just the time for 1 day in seconds. And then we found the change in momentum, our final and initial momentum vectors, as well as our change in velocity. We found F net, dp dt, and we found the components of each of them using the code below. We also found the mass of the black hole using the information from the slide previous. And we printed a series of those masses throughout a bunch of iterations, and we found the average using this code here. And so our final code outputted this here, as you can see, our black hole in our full orbit, and then the final mass of 1.4 times 10 to the 34 kilograms. For part 2, we had the G constant similar to before, the mass of the planet, the moon, the ship, and delta T, and then also our default time of 700 hours. We ended up with negative 19,000 for our X component and 3,900 for our Y component for our initial speed for our ship, and that was found experimentally through trial and error. And then for our net force calculations, we found first the net force on the moon using the combination of the force of the planet on the moon and the force of the ship on the moon, and we added those together to find the net force on the moon. We did that same process for the spaceship, except for the planet and the moon on the ship now. And we found those two, and we applied the Newton's second law and also our update formulas to find the velocity and position of the moon and the ship. And then that resulted in this code where we have our orbit for our starship using, between the moon and the planet. And obviously, again, we did not achieve that stable figure-8, but we did prevent the crashing from happening. So for sources of error, both parts, we just assume that the simulation is not 100% representative of reality just because it is a computer. And we also want to remember that we assume that there are no external forces, so that could be a source of error in terms of assuming that. For part 2 specifically, we have the trial and error is what we use to find the initial velocities, which is inherently is not accurate due to the fact that we're just plugging in numbers. For our what does it mean, we looked at what the difference between net force was, and also the rate of change of momentum and we said that these two are mathematically the same. However, it is easier to find the rate of change of momentum because you only have to focus on the object's velocity and motion, whilst for F net you have to focus on every little combination of net force, of every force that acts upon a body. So for what if we had a system of the black hole, the planet, the moon, and the spaceship, all four, we'd have to find the interacting forces of each one. And the most dominant force would just be the one with the most mass. So in this case, it could be the black hole here. So that's the conclusion of the presentation, where we found the mass of the black hole, and we also mapped out the orbit of the starship.